Welcome to Lecture 1C entitled Graphing of Scalar Functions. And this is the introductory lecture and comes from section 3.6 and 15.1 of the textbooks. The objectives of this teaching module are to essentially develop the tools for sketching scalar functions, which will be required throughout the course. And the main concepts of visualization skills are basically explicit or implicit representation of functions. What do we mean by the domain and range of a function? And then the various approaches for sketching, which include 3D perspective diagrams, traces, and cylinders. And level curves when we're talking about a 2D representation of a 3D problem, which involves two variables, or level surfaces, which is a 3D representation of 4D, which involves three variables. The second slide basically is just an outline of the contents of this particular lecture. It's been itemized here, so there are 13 different topics that we'll cover. I'm not going to go into any detail. This should be self-explanatory.
All right, so first thing we want to do is to look at certain aspects of functions, specifically they relate to multivariable. More or less we'll be dealing with two variables, not likely that we'll do more than two, but the techniques used for more than two variables are similar to what you'll be learning when we do exercises using two variables. So an explicit function is where you can write something in terms of two variables. As if it's a two variable system, then we would say that z is a function of x and y, and I can explicitly write it out as such. So this example would say z equals x squared plus y squared. Now I can take the same function and write it in an implicit form, which means I need to basically bring everything over to one side, which means on the other side it is 0. So for instance, if I subtract z from both sides, then I get x squared plus y squared minus z equals 0. And then I replace that whole group of things on the left, that is x squared plus y squared minus z, by some function f, a function of x, y, z, which I set to 0. So that is the implicit representation of the explicit function above it. Let's now take the case of an implicit function in a very generic sense. So for instance, here I've got sine x, y, z minus zx plus yx equals 0, which I then defined as my function fx, y, z. If I now take this function and go in the opposite direction, it's next to impossible to do it. I need to somehow figure out how to isolate z in that function on the left, which I can't, because there is no way of writing it. I mean, in a power series form, yes, perhaps, but not in that form. So it's really not solvable. Right? So just to keep that in mind. Next thing we would look at is what we mean by the domain and range of a function. And again, we're only dealing with two independent variables, x and y, and some function z equals fxy. So the two definitions are what we mean by domain and what we mean by range. A domain is the permissible values of x and y. And that generally will be values of x and y that are not problematic, as will be shown in the examples to follow. And range are what are the permissible values of z if you put in all the permissible values of x and y. And so there are two different terms that we're dealing with. This can be extended to higher dimensions. So for instance, if we're dealing with three variables, let's say x, y, and z, that would be the domain. And if w is some function of x, y, z, then the range would be permissible values of w. So it can definitely be extended to higher dimensions. All right, so here are some examples of the domain and range. So let's take the first case, z is equal to xy over x minus y. Now if you look at this expression, you realize we're in trouble if x equals y, because you get 0 in the denominator. And so when we choose the domain, we said everything is possible, but please do not choose x equals to y. So we basically say x not equal to y. So if I were to plot on the domain, which means values of x and y, what is permissible, I would essentially show you the picture on the right, but x equals y has to be taken out, which represents the dotted line that you see. So everything excluding the dotted blue line is part of the domain. And the range in this case can be computed. It would be whatever possible values that you can achieve for all possible values of x's and y. Second example would be z is fxy equals the square root of 4 minus x squared minus y squared. In this case, basically, the square root tells us that the argument has to be greater than or equal to 0, otherwise you get an imaginary number. All right, so that means essentially everything contained within a circle of radius r equals 2 is basically within the domain, including the boundary of the circle. Okay, so in this case, you'll see it's a solid blue line, which means it's included the domain. If I don't put a solid line there, it means you can go right up to the edge, but not include the edge. Okay, so it's in or it's out. So in this case, the domain is x squared plus y squared less than or equal to 4, which basically means every point inside the circle, including the boundary of the circle. But the range will be limited. Okay, so the square root of 4 minus x squared minus y squared will basically be limited between the values of z equals 0 and z equals 2. It can't get any smaller than 0, it can't get any larger than 2. The last function, x squared y minus 2xy minus xy squared, there are absolutely no bounds or limits on this function, so x and y can be an element of R2, and z can be an element of R. So this is basically very important, specifically when we move into later lectures dealing with limits, for example. We'll need to be able to understand what is the domain of a function, because within the domain, all sorts of calculations can be done, but we're going to end up with these problematic points where we need to pay careful attention as to how to deal with the function. Okay, so now the next 2 pages are not mandatory. I've put this in as additional information, because when we're dealing with objects typically in this course, they're going to be either planes, hyperboloids, paraboloids, spheres, ellipsoids, some combination of those. And so you really want to get a sort of a feeling what these functions look like. But there's a generic form in which you can put all of these objects, and that's in the form that's shown here. So I've written it out in this form. So this form basically allows me to choose the values of those coefficients in such a way to represent ellipsoids, paraboloids, spheres, hyperboloids, with an arbitrary rotation and translation. In other words, the object might be moved to some location, or it could have been rotated about any axis. This is a very generic form. And so the question would be, how do I get this into a simplified form so that I know precisely what object I'm dealing with? And so this is where it's very handy to move back and forth between a scalar function representation and matrix representation. So if you look here, right, on the second line, and let's say we only care about these terms, we exclude the other terms, then this could be written in the following form. We have a row vector, a matrix, and a column vector. If you do the multiplications here, you'll get that. Why is that convenient? Because we can apply various techniques of linear algebra to essentially make life easy for ourselves. So that's basically what this argument is all about. I'm not going to go into detail. There is a posted handout which you can read. I mean, the key point here is you should go quickly back and review eigenvalues and eigenvectors. And it's been more or less basically procedure that's used here to take these more complex equations and basically convert them into something which is much simpler to work with. And so if you look at the next page, you'll notice here, for instance, that in the end what we're able to do is to take something that was basically very complicated, right, and reduce it down to something which is a little bit easier to work with. For instance, here you'll see this is being replaced by something involving something squared, and something squared is equal to something. So this starts to take on the form of equations that you're familiar with when you're dealing with ellipsoids or paraboloids and things like that. It's basically being rotated to a form where it's more understandable. And these are the different cases I considered in terms of looking at all the different possible objects, just setting the different parameters to values to 0. And there are basically, I guess, 8 combinations in total you consider. And so this is the example for A equals 0. And if you go to page 862, you'll see a sample of the different types of quadratic examples. Anyways, go through it. This is not mandatory. We're not going to be testing you on it, but at least it gives you an understanding as to how you can apply linear algebra from last year, particularly when it comes to doing transformations and making problems a little bit simpler to understand. Okay, so now we're going to look at 3 different techniques for trying to sketch scalar functions. One of them is called a trace, another is a cylinder, and the other is level curves. Now, what is a trace? Well, we draw a 2D cross-sectional view of a 3D graph for a specific plane. And the simplest planes to consider are the x, y, y, z, or zx plane. They do not have to be those planes, but they're generally the easiest ones to work with if we're trying to get an understanding of what the object looks like. So what do we mean by traces? Let's say we have these 3, x, y, y, z, or zx. If we were talking about an xy trace, all we're doing is taking a given function and setting its z value equal to 0. And what we end up with is an equation of a line in the xy plane. On the other hand, if we set y equal to 0, which call that an xz trace, then I get an equation, right, again of a line, but in this case it's going to be in the xz plane. And lastly, if we set x equal to 0, then this becomes a yz trace, which means we're plotting a line in the yz plane. And so 3 different cases to consider. Notice here when we say xz, it's implied that the y equals 0. Okay? So let's take this example here, which is an ellipsoid, x squared over 9 plus y squared over 16 plus z squared over 25 equals 1. So if we're to look at the xy trace, we set z equals 0, then we end up with this expression here. If we're interested in the xz trace, we set y equal to 0, then we end up with the expression here. And if we set x equals 0 in the example function, then we end up with a function that's here. So let's take the first diagram here, and let's look at the xy trace. If we set z equal to 0, that means we end up with a ellipsoid with a major axis and a minor axis. And they're drawn on the xy plane, which is the red line that you see there. So the major axis basically is going to be 4, and the minor axis is 3. Okay, that lies on the plane. All right, so if we move now to B, we can look at the other 2 cases. So we have the red one. Here's the case from the xy trace. And now basically do it for the xz trace and yz trace, and you end up with similar lines, but one of them is on the zx plane and the other one is on the zy plane. So if you take those 3 sketches, looking at them, they form a scaffold. And so from that, you can piece together what the exterior surface would look like. So it's a technique that helps you understand how to sketch it. Do the sketches have to be 100% accurate? No. I think basically you just want to get a sense of what the object looks like. That's the most important thing. All right, if you want to look at an interactive visualization of this, then you can go to the link above, just click on it, and you can play with the object. I think it's more or less self-explanatory. All right, so let's do some more examples. Again, if you want to look at this function and rotate it, you can go to the link here and look at it. So the function is z equals ln y, which is in blue, and I want the zy trace. Okay, so zy trace basically would mean I set x equal to 0. All right, well, there is no x here, but let's make x equal to 0. In that case, basically, what am I dealing with? I'm looking at a line, which occurs at x equals 0, which happens to be on that surface, and it's that red line that you see here. Okay, so that's what I'm plotting. Okay, so that would be the trace. So let's look at another example. All right, so this is an elliptical paraboloid, and before we get into an example in more detail, this is just a sort of handy way of looking at how do you know if it's something opens up or opens down. And so if z is greater than 0, then the elliptical paraboloid opens up, which is this case here. On the other hand, if z is less than 0, the elliptical paraboloid opens down. So you can visualize this here and rotate it, look at it from different points of view, just clicking on this link here. So this problem basically is from chapter 13.6, question 23. And if you want an interactive version of the function, It can be basically obtained by pressing on the link here. The function is y equals x squared over 6 plus z squared over 16. It's the one that's indicated in blue. It's an elliptical paraboloid. And so what we're going to do is look at 4 different traces. We've got xy trace at z equals 0, an xz trace at y equals 0.25, an xz trace at y equals 0, and a yz trace at x equal to 0. So in this case, basically, what would we be doing? We basically setting z equal to 0 in the equation above, and we end up basically graphing y equals x squared over 6. That's on the xy plane, because since z equals 0. For this case here, the xz trace, we would set y equals 0.25, which means you take y and replace it by 0.25, and you'd be solving this equation, which is the equation of a circle. It's equation of an ellipse, but basically it will have a minor axis and a major axis of a specific value. And so this is the one that's shown in black, which is this line that you see here. Thirdly, you've xz trace y equals 0. So again, you just set y equals 0 and you have the equations here, but that only has one solution. That is when xz equals 0, which means it's the point that you see right here at the origin. And lastly, yz trace x equals 0. You set x equal to 0 and you have y equals z squared over 16. And that's indicated by the red line that you see here. All right, so let's do one more example here. So this is the function z equals x squared over 9 minus y squared, which is in blue. And again, if you want to look at the interactive simulation, you can just click on the link there. So let's look at the case of an xy trace with z equals 0. So you set z equal to 0, and you end up with this expression. Xz trace with y equal set to 0, you set y equals 0, and you end up with z equals x squared over 9. And a yz trace, which means you, in this case, set x equal to 0. That means that this is 0, this becomes z equals minus y squared. And so each one of these, which turns out to be a line, is designated in the 3 colors that you see here. All right, so let's look at this one. Xy trace z equals 0, an xz trace y equals 0, and a yz trace x equal to 0. All right, so if we set z equals to 0 here, that means you've got x squared in terms of y squared, or y squared in terms of x squared, which means that you're taking the square root, so you can have 2 possible values, plus or minus 2x in this case. And so that's the line that's shown in yellow. In the case of xz trace y equals 0, let's set the y equal to 0, then that's z equals x squared, and that's the red line. If you set x equals 0 yz trace, then that's z equals minus y squared over 4, and that corresponds to the orange line. All right, so next thing is notion of cylinders. What is that? So cylinder is something which exists if you're given a function, right, and it's missing one of the variables. So if we're talking about a 3D object, okay, and if you look at this here, for example, then it's implied if z is not given that z can be anything. In this case, y is not given, therefore y can be anything. In this case, x is not given, and therefore x can be anything. All right? So this would be more or less taking a function, graphing it, and then extruding it in the direction of the dimension that's been excluded. So in this case, it would be drawing this function, and then basically taking it and stretching it in the direction of the z-axis. So let's take this as an example. X squared plus 4y squared equals 16. Okay, so in this case, basically, it's implied that z can be anything. So if I were to graph that, on the xy plane, that would be basically an ellipse. And so that would be, for instance, the red line that you see there. But since z can be anything, it'd be like taking this ellipse and keep shifting it upwards, any value of z. Well, when you do that, what are you doing? You're extruding out a cylinder, okay? It's an elliptical cylinder in this case. It's not a cylindrical cylinder. So that's what you're doing. So if you take a series of these, one on top of each other, you're basically creating a scaffold. And that scaffold basically allows you to draw the sketch for that function. So in this case, the domain, right, will be such that x is between -4 and 4, right? Y will be between -2 and +2. And as we've mentioned, since z's not included, that means z can be anything. All right, so that's the case when we're dealing with cylinders. This is an interactive version if you want to look at it. I think it should also be self-explanatory. Okay, so the last thing is level curves or level surfaces. Level curves is when we're dealing with a 2-variable function. Level surfaces if we're dealing with a 3-variable function. Why level curves and surfaces under those conditions will be explained shortly. And this is basically the subject of chapter 15.1. So what are level curves? They're projections of the function for different values of z equals fxy onto the xy plane. So if you're given a function z equals xy, then you set z equal to a constant and you plot basically an equation of some form of curve. But it's at a certain given location z. Then you put a different value of z in and redo it. You get another curve. What you do is you put all curves one on top of each other, essentially project on the xy plane, and each curve is given a label corresponding to the value of z chosen. Okay? So that's basically how it's done. Level surfaces are the projections of this function for different values of w equals a function of x, y, z, in this case 3 values, three variables, onto the x, y, z domain. So in this case, w is held constant. If w is held constant, then you basically have x, y, z is equal to a constant value. But that's nothing more than the equation of a surface, okay, and you can put that in implicit form if you wish. So you choose a different value of w, you're choosing a different surface. So you're plotting a series of surfaces, constant surfaces in 3D. All right, so let's do a level curve example. And again, if you want to look at this, you can access it at this URL. And I'm giving you a Gaussian function, which has this form, e to the minus x squared plus y squared. So what do I do, basically, is I set z to different values, which you see here. And I plot basically what the function looks like on the xy plane for different values of z. So you'll see, for instance, the level curve z equals 1 is in blue. Okay, in green is z equals 0.8, and all the way down to z is equal to z equals 0.4 is black, for example. All right, and so here it's a series of pictures. Now notice that z equals blue 1, it turns out to be a dot, because if you want to basically choose 1, the only way that can happen is if x and y is equal to 0, which is at the origin. Otherwise, you end up with just a series of circles. And the other thing you'll notice, for instance, I've chosen these to be equidistant with respect to each other. Okay, these are all equidistant with respect to each other. So what does that mean? That means basically that if I look at how things change, the level curves, the distance between these curves change as the value z changes, you'll notice that it's more or less equidistant here, and then all of a sudden there's a huge gap. So when you see things stretching out, it means the function's getting flatter. On the other hand, if these lines begin bunching up, it means that the equation's getting steeper. And this is best illustrated by means of a topographic map. So here's an example, for instance, that geologists would use. So you see all these various lines here. Each one of these lines represents a constant value of elevation. All right? And they're typically equidistant. So like maybe 100 meters apart, for example. So if you look at this map, it was something interesting. You notice a lot of lines basically in this area. And they're all suddenly compressed and then suddenly widen out. So this would indicate that this is a side of a mountain. Okay, it's either going up or down. You'd have to know what the values of these are to know that. But this obviously is something steep, and out here it looks like it's relatively flat. And if you were to look at a river valley, without knowing a river value, you could basically see that when you see a lot of lines in parallel, on one side and a lot of lines in parallel, or not necessarily parallel, but very, very compressed on the other side. And that tells you you're in a valley. You're going down one side and you're going up the other side. So it's very useful to get a projection of a 3D object onto a plane. All right, so that's something very useful in terms of how it's applied in the outside world. All right, so let's do an example here. Another example, potential function due to 2-point sources. This potential function in xy plane for two 3D point charges. So I'm only considering it in the xy plane. This is just a given. So I've told you that the function is this plus this. And the first thing, of course, I look at is what is the domain of the function? Well, clearly this function blows up if x equals 1 and y equals 0. And this function blows up if x equals 0 and y equals 0. So if you look here, these 2 points have to be excluded. There's the one that you want to get rid of, and that one you have to get rid of. And this is the location of the 2-point charges. Okay, so everything outside of those 2 points is considered within the domain. The value of z is going to be greater than 0 because this is a plus sign and these are positive. Okay, so this is always going to be greater than 0. All right, so that's basically a picture of what to expect. And so now let's look at some level curves for this problem. All right, so again, you can go online. You can look at the URL link here. This is an interactive module where you can select basically your level curves, see where you are. This is an example where we've set the function to 5. So this is a constant value for the value of z. And so that represents this green line that you see here. If you change the value of z, then you get all these different lines that you see here. So very close to this point here, it seems like these are circles. As you get further out, it becomes oblate. And then finally you get this crossover point at some specific value of z. Similarly on this one, close in, it looks like a circle. Anyway, so this gives you an indication what the level curves would look like. And from this you can work backwards to realize that this picture represents this picture on your left. All right, sometimes, again, this is not necessary. I'm just putting this here as information. Sometimes you can simplify a function close to some point. And so just by visually inspection, you'll notice that this is circular. So how can this suddenly become a circle? Or in this region, how can this become a circle? Well, this is what we call asymptotic approximation, where you can make certain assumptions about the nature of the function. So for instance, if this is much, much greater than this, right, which is the case, for instance, if you're very close to this point, this has no impact. This term basically is irrelevant. In which case, basically, you can say that this term basically is going to be small compared to this, so you ignore it. So that means phi equals this. Well, this is nothing more than the equation of a circle. Okay. Similarly, if you were to do it the other way around, where you say that this term is much, much less than this one, then this term becomes dominant. So now it's phi equals this. Well, this is nothing more than the equation of a circle, but displaced, its center displaced along the x-axis by 1 unit. Now, if you get far enough out, way out here somewhere, okay, far, far out, then you can make another approximation if you want, and it is an approximation, right? If x squared plus y squared is much, much, much greater than 1, right, then we can approximate phi as 2 over this expression that you see here. And that would make sense because something out here would look like it has its center at this location, which would be at x equals a half. And it has apparently a somewhat of a circular shape. But the contribution of this one and this one would be more or less the same, and so that's why you see the factor 2 here. Okay, so this is just what the level curves would look like for the 3 different asymptotic cases considered. Okay, so next, level surfaces. What are they? Well, in this case, we would have w is the function x, y, z. So in this example, the function x, y, z is this that you see here, and we set this to a constant, and we graph the function, which would be a surface. Then we choose a different value of w, a constant, and graph it again, which means you get a second surface. So you'll notice here, for different values of w, you're basically graphing different surfaces, and we call them level surfaces. If you want an interactive version of this, you can obtain it by just clicking on the link here. So that concludes Lecture 1D, which is the 4 in the sequence of Lecture 1. Thank you for listening.